Okay, this is another standard organic question where we're given information and we're supposed to figure out what these different molecules are. So there's an element of trial and error as you go through this to try and work it out. And we're told some extra information about a substitution reaction. We get cyanide swapping out the chlorine there, and then reacting to form a carboxylic acid. Now we start with this molecular formula here, and that gets converted with dichromate. So obviously we're thinking about an oxidation reaction going to this. And then we're told some extra information that A, when it's reacted with conch sulfuric, so you're thinking that probably this is an elimination reaction, is going to produce C, D and E, which have this formula C5H9Cl. C has stereoisomers, so there's going to be 4 different groups around one of the carbons. Oh no, sorry, it does not have them. Take care with that. So there are going to be no chiral carbons in there, so there's going to be no carbons which have 4 different groups around them. And C and D and E must be geometric isomers, so that means that we have different groups on each of the carbons with a double bond. So let's start and see if we can work our way through that. Okay, so if we just write this out again, we have A, which we start with, and that undergoes an oxidation reaction here, and that makes C5H9OCl. Now, the fact that we have, just checking that the formula's right there, C5H11, just realised I had the wrong formula there, so I'm just checking that again. Okay. Now, this would seem that if we've got a primary alcohol, we'd go to maybe an aldehyde or a carboxylic acid. The fact that we have less H's there, though, would tend to have us thinking that we've probably got a ketone on the other side, so that we have an OH group here. And we know we've got an OH group because if we have conch sulfuric added, it makes C5H9Cl, and we're talking about geometric isomers. So we know this has got a double bond in it, and it's got a chlorine in it. So if we write out, and we're told that it's a straight chain, so if we've got 5 carbons there, if we put a double bond in this place, we could not have 3 different structures, okay, that could form. So we know that the double bond can't go there. That would mean only one place. Now obviously this is exactly the same as putting it there, so we know the double bond must be in this place. Alright, so you try and limit the trial and error by, thinking clearly about what must be going on here. Now, if we have that there, then we've got to consider now what I was really trying to indicate, of course, is if you had the OH here, that a double bond could only form here. Okay, that's the only place. So that meant that originally you must have had an OH here, and that would mean that you must get a double bond here, but you can also get a double bond here with that major minor thing, the pore getting poorer with elimination. Now, so that really helps us in determining where the OH can be. So we know that's a possibility, and if the OH must be here, because obviously if the OH was here, it would just go on either side. That would mean that the other possibility for this is going to be that. Okay, so get rid of that because it gets removed anyway. And now we've got to consider where we put the chlorine. Now remembering, the chlorine must be in the same place on this molecule as this molecule, because they both started off as A, and they're converted in these, so you cannot put a chlorine in one position to suit requirements and then change it for the other. Okay? Now, if we decide to put the chlorine, for instance, on this carbon here, that would mean that the chlorine must also be on this one here. Now that would mean that this would have a group here. There's obviously an H there which I just haven't drawn in, and there's a number of H's I haven't drawn in, but that would mean this would have 4 different groups, so it can't go there. And the chlorine can also not go here, because as soon as we put it here we're going to have 4 different groups as well. So those are 2 positions it cannot go in. Okay, so it can't go there and it can't go there. Okay, now the chlorine can't go here either, because if this is where the OH is, this is where we're going to get the C double bond O forming with the ketone, so it can't go there either. Also, if we had the chlorine here, this wouldn't be a primary chloroalkane, so it can't go there because that carbon's got 2, and the same would go for this and this one. This is not in a position where it would be a primary chloroalkane, haloalkane, sorry. So that means there's only one place for the chlorine to go, and that's at the end. So that helps us figure out what A is. Okay, now just having drawn this out, this has to be A. We need to have the OH here to as it's a secondary alcohol, so when it gets oxidized it makes this ketone on the other side. That formula, molecular formula, does match up with the one stated in the answers. The chlorine must be here as the requirements are when it talks about a primary chloroalkane, and that's just one of those things to take care of, because it's possible the chlorine could have gone in this position or in this carbon here, which in one of the structures has a double bond as well, and obviously that wouldn't fit the profile of a primary haloalkane. So just make sure you're careful with reading all the information when it comes to working out whether you've got the right structure. So that's A and B. Now this structure here and the structure here are the geometrical isomers. Now I haven't drawn these completely clearly, but obviously we've got these groups on opposite sides, so that would be the trans one, and this one would be on the same side, and this would be the cis one. I've just missed out a H here, so that would be a cis one here. And here we've got the one which isn't a geometrical isomer, and there are no stereoisomers. This can't be a chiral carbon because of the 2 H's, and none of the others can be either. So that's C. So you know, this one is C, and these 2 D and E. Now I'm not sure if we need to tell these apart in terms of cis and trans at the moment, but then we've got to look at F and G. Okay, now just following the guidelines there, now that we've identified A, we can basically do a reaction where we substitute the Cl for Cn, and then through reacting this with sulfuric acid, remembering that carbon is going to replace that, so we're going to actually get an extra carbon which we can see from the C6. So, and that reacts to form carboxylic acid, so 3, 4, 5, 6, so we've still got the OH there. This was the Cn, but is no more, and that's going to be C double bond O, single bond, oops, if I can fit that in there, OH, and then we'll just go through and draw on the rest of the H's, and we have structure F. Okay, so that's structure F, and now we're going to undergo a reaction with concentrated sulfuric acid. So obviously we're thinking about that, removing the OH and the H next to it and forming a double. Now this would seem to be the logical thing to think, that we're going to get a double bond at the end here, and we're going to get either one of these 2 products. The only thing that's wrong with this is that we've ignored the fact that we're talking about a sweet smelling liquid that forms. Now this is a carboxylic acid, and now just the double bond being there isn't going to change it and make it into something that smells nice. And the thing to consider here, and this is where most students would have probably not thought, and is that we've got a carboxylic acid, we've got an alcohol group, and we've got concentrated sulfuric acid. So the sweet smelling liquid was a clue to think that these two could actually combine and make an ester, and not these structures here. Okay, and also that would have been two possibilities here. Okay, whereas this is only one possibility up here. So that would have meant there would have been two possibilities for G, and that's not the case, and it doesn't follow the criteria. This would be tricky. So we just need to redraw that, and obviously that means we're going to end up with a ring structure. We just have to make sure we get that right. Now we're drawing it, just taking sure to make sure we put the H's in there as well. This is the ester, and this is structure G that meets those criteria. Okay. Now you need to explain a little bit about how you've done that, but basically there's a little bit of trial and error here, of course, but and just paying attention to every bit of information. For instance, that ester bit at the end would have been easy to miss. All right, and that's that question.